So we're gonna change things up a bit this time because we're recording a series, and series are more interesting if you can listen to them quicker, right? So what we're gonna do for our series is we run them every week, and new topics come bi-weekly. So for this series, you can expect another episode next week. Exciting.
Okay, so let's go. Hello and welcome to yet another episode of What on Earth podcast. I'm Veronica, and with me, as always, is my co host Tika. Hi, Tika!
Hello, everyone.
And we record at the beginning of a spooky season. And what's more spooky than vast and cold space, which holds all the cool stuff like planets and stars and moons and black holes. So today's episode, we dive deep to answer one question: what on earth is solar system? And solar system, of course, is our home. It's the place where our planet orbits around the sun, and the sun is our star, the major star. Beginning with answering question where we get our knowledge about the deep space, because it's not that we can observe everything. We can only see certain parts of space, but we take our information from, for example, meteorites, which are preserved relics of the early solar system material with those interplanetary dust particles. We can collect them with our spaceships. And these are the fragments of rocks and metal from other bodies in the solar system that had either fallen on Earth and survived the passage through atmosphere, or we collected them from interplanetary space. We can also use Moon because it's the natural laboratory for, let's say, planetary formation. It's a planetary body different from Earth, which actually we visited, and we have quite okay understanding of how it's formed. We also have numerical simulations like N-body and impact models, which are using all the equations like equation of state and stuff like that to simulate what happens to a body if it's hit by another body or how it was forming. Then we, of course, have quite classical astronomical observations. We can observe with gigantic telescopes, and we right now also have telescopes which we put on our orbits, like, for example, Hubble telescope. Then, of course, we have a more sophisticated stuff like isotopic and chemical analysis of meteorites and those samples that we collected. And we should begin this story with formation of the sun itself. And the sun, or stars, because our sun is a star, actually form in something which we call star nebula. And nebulas are kind of cradles of stars, so where the stars are being born. And in general, they are dense patches of hydrogen and helium, which are in space. And everything generally in universe we like to operate of like equilibrium, so everything is in perfect balance. So when we have the hydrogen and helium floating through space in perfect equilibrium, there is this pressure which gas generally produces, and it's counterbalanced by a gravitational pressure, because even small particles have certain like gravity, and it's the same with pressure. Certain gases create pressure. And as long as this is in balance, it's fine. But sometimes the gravity starts to outweigh the pressure of the gas. So it's the outward pressure is being less than the inward pressure. And then above certain limit, which we called Jean's mass, the gravity will collapse. And what I mean by collapsing, it means that it starts to condense and start going inward. So the particles start being aggregated and starts to creating more and more and more gravity. And then generally the matter becomes hotter and hotter, and over millions and millions of years, the atoms will be ionized into plasma.
Yeah, so if I understand correctly, these particles somehow get out of an equilibrium and then consolidate together or move towards each other because of gravity, and then gravity gets bigger and bigger and more particles
Heavier and heavier.
join?
Yes.
So it's a party.
It's a party, yeah. So literally it's
Party
like
of matter.
we actually also, there's several theories how we even trigger this collapse. Because, this collapse, it's not necessarily happening out of nowhere. It could be like you have this nebulae of gas, and then you have somewhere supernova, and then just rippling through, you will trigger the collapse of gravity.
Yeah, but it takes a long, long time
It
for it
takes
to
a
get
long
anywhere
time.
close.
Yes, because like, for example, at the very beginning, um, even though you have a quite hotter protostar, it's still not hot enough to start fusion. So it will just condense, and eventually you will create plasma. It's like very much simplification.
And then you have a sun
And then you
or
have
a star.
you born a star.
A star is
The
born.
star is born.
Nice.
Yeah, so like I said, the inner region of the plasma is so hot that the outward pressure prevents the further collapse from gravity. And this is the protostar, which is again in temporary equilibrium. And then if the system is just single star, it's called T Tauri or pre-main sequence star. And then generally more material collects around the star, and then even more mass is falling inward together. And the pressure increases. The T Tauri is generally hot, millions of degrees, and then you get nuclear fusion. So then you actually have like the birth of the star. This is where we can start talking about the star.
So where does all this star stuff come from? Is it just floating around in like space, in a very large space?
Yeah.
Yeah.
Yeah, so that's a great question. Generally, hydrogen and helium is abundant in space. But all the other particles, which will be key ingredients, let's say, to cook planets, are often coming also from previous stars. So this is like older generation of stars. And then through nova and supernova, they release all the material into space, which then can be aggregated. Yeah, and then if we talk about the T Tauri stars, they are generally much brighter than the oldest stars, like the sun, because they release the gravitational energy as the star contracts. So they are much, much, much brighter. And then the initial collapse of the cloud, so the molecular cloud or the nebula cloud, takes roughly 100,000 years. And then, like I said, the original triggered collapse theory was based on the sequencing found in the ages of stars in close proximity. Because generally, when you see the molecular cloud or the nebulae, it's not only one star being born at the same time. You kind of see a sequence of stars being born one after another, and that's why you kind of think about it that it was triggered by some kind of wave.
That's pretty fast, right? 100,000
In
years. If
a
you
scale of things,
remember the millions.
yeah, in a scale of things, it's quite fast. And of course, like when we have the gravity, and all the material around, you start flattening it because it's kind of like you start spinning it like pizza dough, and then it gets flatter. And then generally the mass around the star, which is rotating, starts to be flat and like disc-like. So this is the cradle of solar system. And
So it's because of the speed of the twist, right? It just gets
yes, it's
spread
generally the
out to the outer rims.
rotational movement, and then it just gets flattened like a pizza dough. And then this kind of evolution, when you have this, spinning of the whole protoplanetary disk, is why the current planets only hold like 0.1% of the mass of the solar system, but they retain the 99% of its angular momentum. And the mass is, of course, in the sun itself, and the angular momentum is there.
So basically everything important has been thrown away, flown out of this disk. And the disk was the galaxy, right? Or was it the sun?
So we are right now talking about just our solar system. So just to kind of give you overview, we are one of like 100 to 100 billion stars. Like our sun is one of 100 to 100 billion stars just within our Milky Way, which is the galaxy what we are in. And there are millions and billions of other galaxies in space. So it's kind of pretty crazy to think about that we are so really not relevant. So next time you have a beef with someone, just think about it. how irrelevant it is in the midst of it all. Like, it's really, we are just super tiny. We don't matter at all.
Well, good to know. Thank you.
Nothing matters. We are just dust particle floating through space, literally, kind of. Because like every atom, I mean, probably people will know that, but like if don't, this is actually kind of cool because we are literally made from dying stars. So every single thing which is like heavier, I think, than helium had to come from nuclear fusion. And nuclear fusion is just smooshing atoms together so much that they are actually creating different atoms, to very much oversimplify. So everything heavier than the initial hydrogen and helium had to come or be born within the star, and then this is released within the supernova, and then it's aggregated again and again and again into, our planet and our everything. So everything we made as humans came from dying stars. It's kind of really cool. I really like. But going back to our story, so we are in the moment when the star was born, but we were not born yet. We are still at the stage when we are dust in the wind, literally. We are just spinning cloud of nothingness. And those tiny dust particles, which are spinning in this protoplanetary disk, and it's actually very cool because with our telescope we have right now, like Hubble telescope, we can actually see this happening live. So we see different protoplanetary disks being born and different small solar system being born. And then we can see it literally as a star, flat dough of pizza, and then tiny rims of, planets being born. And this is what happened with us. So initial dust particles started to collide with each other and clump together into rocks. And those rocks started smooshing with each other into planetesimals, which were over thousands of years. They were shaped by gravity and by spinning motions and by collisions with each other into spherical protoplanets. And those protoplanets generally aggregated together, but eventually they coordinated each other, or like they cleared everything out of their way and formed planets as we know.
Yeah, because all these balls make their own gravity, right? So it all clumps.
Exactly. They
It all
start
clumps
clumping,
together.
it's kind of like a snowball effect, right? So you have something like a seed which starts to rotate. It rotates around itself, but it also starts, also rotates around the sun. And then eventually it clears out everything which is on its way around as it orbits.
They don't like space messy like we do.
No, they like to very much organized. Although it gets messy sometimes. It was very violent at the very beginning. There was a lot of, giant impacts and stuff like that. It was pretty brutal time to be not alive, but to be to be a
There's no way to
planetesimal.
be alive in such a system.
Yeah, it's pretty brutal to be a planetesimal in the early beginning of solar system.
I mean, it's the same for humans, right? If you're young, it's very brutal to be alive.
Yeah, you have to fight for your space, exactly.
You get dented on the way. It's fine.
Yeah, and which one cooler feature about the protoplanetary disk is that it has this certain gradient, and it then later on it's manifests itself uh, in the division between the rocky planets that we are be talking about and the gas and ice giants. And it's because, the outwards, as much as you go out of the sun, it becomes hotter, less hot. So it becomes colder and colder. So all the particles which are like heavier and whatever, they kind of accumulate closer to the sun, and everything which is lighter, like helium and hydrogen, it's generally more outside of the planetary disk. So that's why we have the gradation, which is the very stark contrast we see in the planet's formation. And our solar system formed 4.6 billion years ago, and then likely within the molecular cloud, similar to the Orion Nebula, we can Google very beautiful pictures of Orion Nebula. And they are very cool. I actually, when I was a kid, I loved the pictures of like nebulas. They are just fantastic. They are like art itself, better than art itself. And the primitive stardust from this nebula, it's actually, we can sample it and we can test it because it was preserved within meteorites. And they're literally pieces of pre-solar system materials that we can test. That's why we kind of know how old the solar system is, because we tested it through meteorites, which is absolutely mind-blowing that you have those, like, very old, ancient pieces of rock just flying around. And these are literally stuff from the beginning of the solar system. I mean, it's mind-blowing. Like, it's literally mind-blowing.
So this beginning, what does it look like exactly? So you were saying there were processes of a very long time, and then at one point planets formed, but there was still a lot of stuff floating around. Like when this 4.6 billion years mark, what would you say? How would you describe what it looked like?
So the 4.6 billion years is this kind of the formation of the solar system as we kind of would describe now. So we have our sun established, and then our planets start being, formed. It's not that everything been static since 4.6 billion years, because that's not true. You will soon, I will talk about it a bit, that the orbit slightly adjusted itself, especially for the gas giants, which triggered some meteorite showers, which were called giant, like the heavy bombardment period, which we can definitely see a lot of it on the moon. Most of the moon craters were created during heavy bombardments. It also added around like 1% of the mass of the moon to itself, just merged together. That's a lot of mass. And we also see it, the signature, we also see it on Earth. We call it the late veneer, which is like the added material later on after Earth was formed, and we can see it as an isotopic signature. We can catch it actually, so it's pretty impressive. And then, since we already said that our solar system at this point was formed into what we more or less now know, maybe we should talk a bit about how it looks like now. So the architecture of our solar system. So
Take me with you.
buckle up. We of course start at the sun. I think it's a hot take. We're gonna start at the sun.
Hot take. Nice.
Our sun is a typical yellow main sequence G star, and this is like very fancy nomenclature, but it boils down. And we're gonna maybe talk about it a bit later. We're gonna do bonus episode about that when we will be talking just about stars. But I will just the classification to kind of run it down to you. When we talk about G star, we talk about yellow star. So there's a certain letters which we add colors to it. And then of course the temperature of the star is correlated with the color. And then you can plot it together, and then it creates this kind of trend. And this trend is called sequence. So if it follows the sequence, we call it the main sequence. And yeah, our sun, like we said, it's 4.6 billion years old, and it's pretty new for universe standards. And we are about halfway time of its lifetime. So we still have like 5 billion years to go.
So does that mean as humans also have 5 billion years, or are we not going to survive halfway through?
Oh,
Like how does the sun's age impact survival rates at Earth, I would say?
yeah. So we are definitely not going to see it through because eventually, as the star is being born, mature, burned out, and die, it changes its size. And as our star will eventually expand to be like a red giant, we're just gonna die.
Well, good news for us.
Good, bad news for us. But yeah, I don't think our civilization, as we know, or maybe I'm wrong, but I don't think, given our previous record, like mass extinction, more, Tika, about that. I don't think we're gonna be there to witness that. And how do we know that the sun is 4.5 billion years, because that's kind of also interesting, right? We have the record of the meteorites. We know that it was born 4.6 or 4.5 billion years ago. And also, this is pretty interesting. Our sun is actually stratified, it's like a planet, but much hotter.
So it's like an onion.
Like an
It has
onion.
layers.
It has layers.
Is this a Shrek reference, please?
Yes. So yeah, star, just like ogres, have layers.
Nice.
The photosphere is the outer layer, and it has like 6,000 Kelvin degrees, and the inner part is like way hotter because it says 15 million kelvins. And generally, what sun is doing, it's not burning because it doesn't have oxygen, so there's no combustion. But what it actually is doing, it's, I know, English is very limited language for that, is shining. Because it's actually producing, the state of the matter is so hot that it's actually plasma. And this is state of matter beyond gas state, where it's just too hot for electrons to be coordinated to atoms. And it's just kind of like this nuclei soup. And the nuclei is this positively charged central region of atom composed of like proton. And then, for all of the atoms except hydrogen, one or more neutrons. And it generally contains most of the mass of the atom. This is the nuclei. And they are just like floating around, and, the electrons flying just around. And then, the hotter it gets, the more inner it gets, it starts to be smooshed together. And generally, to be very simplified, the nuclear fusion, what it does is just smooshes this together, and the energy of 2 hydrogen is actually less. It's more to be separate, and it's less when it's helium. So it's energetically more favored to be together, and the difference in energy is being released as the heat we see.
Okay,
As
so it's
energy.
like a couple of people. They are stressed when apart and calm when together.
It's much more energetically favored to be together, yes.
Okay. I agree. It's the same with helium.
Yeah, it's the same with helium.
Nice.
And then the photon emissions, which is the energy, it takes around 100,000 years before it finds the surface. So once we have the nuclear fusion and the energy are being released after the nuclear fusion, after those two atoms smooshing together, it finds its surface eventually, and then we see the light or the photons. Then, of course, it has this beautiful corona, and it says like 1 million Kelvin, which is actually hotter than the photosphere or chromosphere. The corona, usually you can see it when we have a sun eclipse. We can see when we have a solar eclipse, and this is usually just this rim around it. Then we have the sunspots, which you might heard about, and this is where the magnetic sphere loops out of the sun, because of course sun produces massive magnetic field. And then we have the solar flares that you might heard about because of the beautiful consequences of it, which is aurora or northern lights, and the solar wind, which is a constant stream of high energy particles which is emitted by the corona. And then the solar wind is actually super interesting because it defines the boundaries of the solar system, because it travels at the incredible distance, and it kind of marks the sun limit of influence of its surrounding. And the Voyager 1 space mission detected the terminal shock at around 94 astronomical units. An astronomical unit is the distance between sun and the Earth. And then also the subsonic speed of this wind, solar wind, because it travels at a sonic speed, like up to 50 astronomical units further. So it's like, 40 astronomical unit big, our solar system. So it's pretty damn big. I mean, in the scheme of things, it's not, but like in our understanding, it's pretty extensive.
That we can even measure it marvels me.
Thank you guys for listening. We're gonna cut short here because we have quite a long episode already. But remember to stick with us because in next episode we're gonna continue with our space journey. Most importantly, keep asking yourself,
What on earth